Hello, this video is for Module 1, Part 2, and includes a discussion of simple linear regression as a predictive analytics tool. Okay, let's go ahead and get started then. So as I said, Module 1, Part 2 is for simple linear regression. Simple linear regression is used to understand the relationship between a response variable and one predictor variable. A simple linear regression analysis will allow us to make predictions for a response using a predictor variable. Now, there will be situations where you may have several predictor variables, and we call that multiple linear regression, and that's going to be discussed in Module 1, Part 3. Okay, let's consider our example here for this module. We're going to be looking at data from the Centers for Medicare and Medicaid Services on complications and deaths from nearly 4,850 different hospitals across the United States. This information comes from the Centers for Medicare and Medicaid Services website, which is here. And then I provided also a link directly to the data that I am using here for this module. And that is here. You can see this is complications and deaths for hospitals across the United States. There's information about the data dictionary here, and you can download the entire data set here if you want. I have done that already and put that in our files folder for us. I've done a little bit of cleaning. I've done a little bit of cleaning to that data, so you can access that here from our files folder. Also in this files folder is the associated Colab document for this handout. You can get a copy of that by just clicking on that. Remember, with our Colab documents, we're going to want to copy to drive so that I have my own copy of this Colab document. Once I do that, then I'm able to run the code here for this particular module. So again, hitting the run button for each of these code chunks will execute the code that is present in that code chunk. You do need to run these in succession. So what I mean by that is you're not able to jump down to a code chunk way down here without running the ones before. There is a decent amount of data management that needs to be done with this data before that we can do any plotting and also any modeling with this data. So here, for example, is doing some cleaning up of the data. Down below here, I have information on how to create like the map that we have in the notes, and then getting the regression output and a lot of the different scatter plots, etc. So I'm not going to go through and run all the code in this module, but this is the code that was used to create the notes here. Okay, so let's talk a little bit about the fields that are of particular interest in this module here. And that's going to be just the state. So I'm going to do my regression analysis on just a subset of all of the hospitals. In particular, my regression analysis is going to be just on the facilities in Minnesota. For the task, I'm going to have you look at the hospitals in Michigan. Some of the measures that I'm going to be looking at are PSI 90, which is a patient safety and adverse events composite score or measure. And we want this value or this quantity to be low. That is better to have a low PSI 90 score. That's going to be my response variable throughout this module. I'm going to try to predict or understand this safety and adverse composite score using PSI03, which is pressure ulcer rate. Pressure ulcers are just your bed sores, and this rate is at a per 1,000 discharges. And again, a lower value is better here. Here's an example of what the data looks like. I have just captured information from 2 of the roughly 4,850 hospitals here. The measure ID are the different measures or characteristics being measured on this particular hospital. There's a total of 19 different measures for each hospital. We can see the PSI 90, which I am going to be investigating here. And I'm going to be using PSI 03 to try to understand PSI 90. All of this information just repeats itself for a different hospital here. So you notice that the first one is the Southeast Health Medical Center in Alabama. This next set is the Marshall Medical Centers in Alabama. And this just goes down, all the way down. It actually is somewhat large, has about 90,000 rows because I have 4,850 hospitals. And for each hospital, I have 19 different measures. So again, I've cleaned up that data for you or provided the code to clean up that data. Here, before I get started into my simple linear regression analysis, I'm just doing a map of the PSI 90 measures. Again, this is that patient safety measure. Red is bad here. So it looks like Delaware here is quite red. Alaska has a pretty dark shade of red, and even New Mexico and North Dakota there. New York is fairly red. I do have some that are on the low end here of this patient safety measure. So hospitals in Washington and Oregon are fairly low in that PS90 score. Utah here, what is that? New Hampshire, I think that is fairly low. Now there is certainly going to be variation within each state as well. So some of the hospitals within Minnesota are going to be higher than other hospitals within Minnesota. And that's just based on the different demographics of where that particular hospital is located, things like that. But this just gives us kind of an overview of what's going on with that PS90 measure, at least comparing states to one another. Okay, so how do I conduct a simple linear regression analysis then? This is done using certainly our computing technologies. We don't want to do this work by hand. So I'm going to be using R to do that, but you can use other software packages as well. Again, a regression analysis is used to provide details regarding the relationship between the response and one or more predictor variables. If I'm doing a simple linear regression, that just means I have one predictor variable here. So the setup for my regression analysis here is going to be, I'm only going to be looking at hospitals in Minnesota. My response is that composite measure for patient safety, that PSI 90 score. And the variable that I'm going to use to try to understand my response is the pressure ulcer rate, which is that PSI 03 score. Okay, let's look at this scatter plot. So that's the first thing that we usually do when we begin a regression analysis, is just to visually look at the data. On the scatter plot, we have the y-axis is always the response variable, and the x-axis is always going to be your predictor variable. Some observations that I see when I look at this plot is that as the pressure ulcer rate goes up, I can see that the composite score for patient safety goes up as well. So there is an increasing trend or a positive trend in this scatter plot. I want to be down here in this lower left corner, because this is where the patient safety composite measure is low, and also the pressure ulcer rate is low. Hospitals up here have a high pressure ulcer rate, and they also have a high composite score for patient quality or patient safety. And that's bad to be up here in the high end there. I have identified some of the hospitals here from Minnesota that are in this plot. So the one down here in the very lower left corner is St. Cloud. I have the Mayo Clinic in Mankato here. So St. Cloud and Mayo Clinic Mankato have about the same pressure ulcer rate, around, about 0.15 or so. But the St. Cloud Hospital has a considerably lower score for their patient safety. St. Cloud is down here at about 0.75 or so, whereas Mayo Clinic Mankato is up around 0.95. Here's another hospital, St. Francis Regional Medical Center. This point is very close to the trend line here, which is going to be used to make my predictions. So the actual PSI 90 rate is going to be very close to the predicted PSI 90 rate for that particular hospital. North Memorial looks like they have the highest here pressure ulcer rate of all the hospitals in Minnesota. And they have a somewhat high PS 90 score as well. North Memorial Health is going to have a prediction that is higher. So the predicted value here is going to be at the line. Their predicted value for North Memorial Health Hospital will be higher than their actual score here. So this particular hospital will end up with a slight over prediction in their PSI 90 rate. Okay, let's talk a little bit about the regression output. The simple linear regression model can be fit, as I said, using a variety of computing technologies. The syntax that I am showing you here is for R, which is being run in Colab. If you were to run this using Python or other computing technologies, it's going to be somewhat similar to this. This here is what we call the model object. So this is the process that I'm going to use to fit the model, and that information gets put into the model object here. So both R and Python are built using objects. And because this is a simple linear regression model, then this is a model object here. The LM is just the algorithm, it is the function that contains the algorithm for actually fitting the model. What information do I have to pass to that algorithm is two things: the data. Okay, so I am getting, again, the data from Minnesota here. And then also information about the structure of the prediction equation that you are using. The syntax here for R is to use the response tilde, and then on the right side of the tilde are the predictor variables. Here I just have one predictor variable because I'm doing simple linear regression. But if I had more than one, I would just add a plus sign here and then just add a second predictor variable in that formula. So this is a somewhat different syntax. They don't use the equal sign here because that would be confusing to the code relative to these other equal signs that are present. So instead they just use a tilde there for that equation. But again, on the left side of that is the response, and on the right side of that is any predictor variables that you have. Here's what the simple linear regression output looks like in R. And then here's what the simple linear regression output looks like in JUMP. JUMP is a statistical software package that we use extensively here at Winona State University. So I'm just showing you that for comparisons. Now the output here is very similar. So I have output under estimates. I have things called R squared. And then I have quantities like the root mean square error, or R calls that the residual standard error. So the four values that I have here are going to be discussed in detail. That I have highlighted here will be discussed in detail. Let us first consider the prediction formula. The prediction formula is just obtained under the estimates here. So the first one here is the y-intercept at 0.80. And then this is going to be the slope for PSI03, and that's going to be 0.32 if I round that. So that's how I got this prediction equation. Talk a little bit about let's do the y-intercept maybe. If the PSI03 were 0, then I would put, what would the equation be? It would be 0.32 times 0. So this part is going to go away, and you're just going to be left with this equation. So that is going to be the 0.80, or the y-intercept is going to be the predicted PSI90 score when the PSI03 rate is at 0. So visually, if the PSI03 rate is down here at 0, if there wasn't any bed sores or pressure ulcer rates here, I would expect the PSI90 score to be about 0.8. So the PSI90 is a composite score that includes things other than just PSI03. You have like sepsis rate goes into that. There's several different measures that go into this composite score. We're just trying to understand the composite score here using just the pressure ulcers. So again, the 0.80 is the y-intercept, and that is where the PSI90 value would be if the PSI03 rate were 0. Now we do have to be careful in interpreting that, because we need to ask ourselves, is it reasonable to have a PSI03 value near 0 or at 0? I mean, that is the optimal goal there, but it looks like the lowest here out of all the hospitals in Minnesota is about 0.15 or so. So it doesn't reach down below that. So we want to be careful in trying to make interpretations outside of the range of the data that we have. We call that extrapolating, and we don't want to do that. So oftentimes, when we're trying to understand the y-intercept, we are actually extrapolating, that is going beyond the range of our data. So we do want to be careful in whether or not that's actually practically significant or useful. On the other hand, the slope is always useful, because that tells me, well, what is the slope? The slope is simply the rise over the run. So if I run 1, I'm going to rise 0.32. That's what the slope is of this equation. So let's suppose that I have one hospital, let's call it Hospital A, that has a PSI03 rate of 0.25. I have another hospital that is Hospital B, and let's suppose their PSI03 rate is 1.25. I can expect Hospital B to be higher for the PSI90. Okay, it looks like for Hospital B, PSI90 is going to be about 1.2. But for Hospital A, PSI90, I would expect it to be about 0.88. The slope here, the 0.32, is just that increase in the PSI90 score that I can expect for Hospital B over Hospital A. So this is how much the Y is going to increase for each 1 unit increase in the predictor variable. Okay, let's talk about the quality of the predictions. The R-squared is used to measure the quality of the predictions. So the R-squared value here is 0.6894. Looks like R calls it the multiple R-squared, but it's the 0.6894. The R-squared's values range from 0 to 1, or from 0% to 100%. If the R-squared value is at 100%, this plot would have all of the dots right on top of the green line, which means all of my predictions are very close or actually on the actual PSI. So the amount of agreement between the actual and predicted PSI is very, very high when the R-squared is near 1. If the R-squared is near 0, these points are just going to be kind of scattered all over the place, and there's not going to be any agreement between the actual and the predicted. So the R-squared quantity ranges from 0 to 1. Here I have an R-squared value of 69%, which is pretty good. That's pretty high. There is a more technical interpretation of R-squared that's commonly used by statisticians. And that interpretation is as follows, that 69% of the variation in this composite measure for patient safety can be explained using the simple linear regression model with this predictor. Okay, so let's go back up here and look at where's my scatter plot here? So notice that the PSI 90 has variation in it. There's an up and down spread here in these dots. 69% of that variation can be explained using my trend line and this predictor variable here. So again, that is quite a bit of, that 69% of the variation can be understood using this predictor. If the R-squared is 100%, what that means is 100% of the variation in my response can be explained by my predictor. And in that situation, again, we're going to have perfect predictions. So we want a higher R-squared in these models. Let's look at some of the points that we highlighted before here. And again, I'm looking at the predicted versus the actual plot here. When we're looking at that plot, I should have mentioned this, but this is the y = x line in this plot. So the y is the actual, the x is predicted. We want the points to fall close to this y = x line. So let's point out some of the points that are close here. Here's that St. Francis Hospital. Again, it is close to the y = x line on this plot. So all of these here in group B, and there's other ones down here that fall real close to the line, what that tells us is that the model is accurately predicting the PSI 90 score for these hospitals. This group of points here, I called them group A, and St. Cloud sits in this group. We can see that the predicted values for this group are higher than the actual values. Predicted values are around, 0.85 up to 0.9, whereas the actual values are from about 0.75 to 0.8. So all of the points here, okay, or all of the hospitals here are going to be over-predicted. The model's going to over-predict for those. It's a little counterintuitive because it's under the line. But again, that means that they are the prediction, we would predict them to be up here, but they're actually down here, so they're over-predicted. This point here is badly under-predicted because it's a long ways from that y = x line. So this particular hospital here just has one data point in it, and I'm calling that group C. How do I make predictions? Well, in order to make predictions, all we need to do is to obtain the PSI 03 rate for each of the hospitals. So I have 3 hospitals picked out here, some of them that I identified up above. So for example, for St. Cloud Hospital, I have a PSI 03 rate of 0.15. I would just plug that into the equation up above to get a predicted PSI 90 score. So I just plug that 0.15 right in here for the PSI 03. And when I do that, I get a value of 0.8480. This is going to, as I said earlier, for St. Cloud, I'm going to be over-predicting. The amount that I'm off is simply called the prediction error. So the prediction error is just the actual value minus the predicted, which is going to be about negative 0.12 or so here. A negative prediction error means that my predicted value is higher than my actual value. So a negative prediction error means that I over-predicted. On the other hand, the Mayo Clinic Mankato Hospital has a PSI score of about 0.14. So plugging that into the equation, I get a predicted value of about 0.84 50 or so, their actual value is higher than this prediction. So Mayo Clinic Health System, for some reason, has a higher composite patient safety score than what I would expect. If I do the prediction error for that, I'm going to end up with a positive 0.1152. The St. Francis Hospital was the one that was really close to the trend line. Let's look at that real quickly again. So I would anticipate that the prediction and the actual to be real close to one another. The PSI 90 score, the PSI 03 score for St. Francis is considerably higher than each of those previous hospitals at 0.87. Plugging that into the equation is certainly, oh, there's a typo there. I'll fix that for you. I'll go ahead and hit pause actually in the video, and I'll just be right back. Okay, so for the St. Francis Regional Hospital, I would just plug in the PSI 03 value of 0.87 into that equation. You can see that the prediction is real close to the actual here, so the prediction error is actually going to be real close to 0. Okay, so how do I measure prediction error? Or you can see that I get a prediction error for every single hospital. How do I go about measuring what a typical amount of prediction error is? One of these we've already talked about in the previous module, and that is the mean absolute prediction error. There is a second one that is more common, at least when you are thinking about statistical modeling, and that is the root mean square error. Okay, so the root mean square error, or the RMSE, is almost always given automatically when you conduct a regression analysis. So where's my regression output again? You can see that the root mean square error here, that value of 0.0696 is given to me automatically. So the root mean square error is just looking at those prediction errors, squaring them, and then dividing by n-2, and then taking the square root. Now the use of n-2 in the denominator is appropriate when I'm doing simple linear regression. The model has to estimate the y-intercept and the slope, so that's why I'm subtracting 2. If you had 2 predictive variables, then what the model has to do is estimate 2 different slopes and the y-intercept, so I would use n-3 in the denominator. Now, oftentimes when we do predictive modeling, there's a large number of observations that we are using. So using n-2 in the denominator versus n, in practice has a minimal effect on the value of this metric. The mean absolute prediction error is not automatically provided by most computing technologies. However, we can easily compute that. And that is shown in our associated Colab document. For this particular problem, it looks like the RMSE value, if we were to round that, is close to 0.07. Whereas my MAPE, or my mean absolute prediction error, is about 0.05. Turns out for this example that the root mean square error is a little bit larger than the mean absolute prediction error, but that's not always going to be the case. There isn't a large number of observations here. Again, these are hospitals across Minnesota. I have a total of 48 here in this particular example. So that's one reason that these values are a little bit different than one another. Generally speaking, though, the PSI 90 scores range from about 0.7 up to about 1.3. And the average error here of 0.05, or if you were to use RMSE, the average error is about 0.07. That's pretty small relative to the PSI 90 values. This model, again, is doing pretty good in terms of the predictions. Let's go ahead and look at a scatter plot of the prediction errors. This is sometimes referred to as a residual plot. Here I have the predicted values on the x-axis again, but on the y-axis I have the prediction errors. And I want the prediction errors to be close to 0, So there's again my green line here going across. If the prediction errors are close to 0, okay, that means the model is accurately predicting for those observations. If my points sit below, okay, if I have a negative prediction error, that means I've over-predicted with the model. And this is that point, again, that was badly under-predicted. Okay, so that should say under-predicted there. I apologize. I will again pause the video and fix that. Okay. So again, observations where the prediction errors are positive are going to be hospitals for which the model under-predicted. The average amount of prediction error, again measured by either the root mean square error or the MAPE, the mean absolute prediction error, is just the average distance of these dots to the horizontal line there. Let us consider some of the points that we identified earlier. Group B were points for which the predictions were very good, and the prediction errors here are going to be close to 0. Group A had negative prediction errors, and Group C up here had positive prediction errors. Another thing that I could do is to simply rank the prediction errors from largest positive values to the largest negative values. So that's what I've done here with, I guess I've identified 3 different lists here. List number 1 is where the prediction errors are large and positive. List number 2 are where the prediction errors are pretty close to 0. And then list number 3 are where the prediction errors are very negative. So let's look at some of the positive prediction errors. Positive prediction errors are going to be bad in the sense that the actual PSI 90 score for these hospitals are going to be considerably higher than what we would expect them to be when I'm basing these predictions off the pressure ulcer rate. So for Mayo Health System's Albert Lea and Austin, we can see that their pressure ulcer rate is 0.32. I would expect, based on information from all the hospitals in Minnesota, I would expect their PSI 90 score to be about 0.9. However, their actual score is 1.11, which is considerably higher than what I would expect. So their prediction error here is positive. So in some sense, these hospitals are doing worse than I would expect them to do. These hospitals here in list 2, you can see that the predicted PSI 90 scores are really close to their actual PSI 90 scores. And as a result, their errors are going to be very small. In fact, for District 1 hospital, I was able to make an exact prediction for that hospital, at least out to 4 decimal places. List number 3 includes places where the predicted PSI 90 score is actually higher than their actual score. So for, let's say, St. Cloud Hospital, their actual score was 0.73. I predicted their PSI 90 score to be about 0.85. So they're actually under what I would anticipate their PSI 90 score to be given their PSI 03 rate. So negative prediction errors here in this particular context are good. Some final thoughts here. There are 2 main approaches when I'm fitting or doing modeling. So when I'm fitting a model or doing modeling. The first is to obtain a model to understand the relationship between the response and the predictor variables. Okay, that's kind of your classical statistical modeling, is to really try to discover the relationship between those 2 variables. Predictive analytics, though, usually is more concerned about just trying to obtain the best possible predictions. So that's kind of our classical machine learning idea, is just to go after the best possible predictions. Now, the techniques that we use for these two different approaches do vary. Some argue, including myself, that the data used to measure the predictive ability of a model should not also be used to build the model. So there is something called cross-validation. Cross-validation is a technique in which the data is split into two parts. A training set, which usually consists of a 70 to 80% of the data, is used to build the model, and then a test set, which contains the other 20 to 30% of the data, is used to evaluate the predictions. Cross-validation provides a better idea of the true predictive ability of a model. And this concept will be discussed later in this course. It wasn't used here, but we will talk about that later in the course. Okay, let's talk about your task then. The task simply has you look at the information, again, between PSI 90 and PSI 03 for hospitals in Michigan. Okay, so I have kind of our standard output here, or our scatter plot to start with. I have our regression output with some questions for you. Here's the actual versus predicted scatter plot with a couple of questions. Here's our prediction errors plot to understand our prediction errors with a couple of questions. And then I provided a couple of lists regarding the prediction errors. And I have a couple of questions regarding that list there that I've provided to you. Okay, that does it then for Module 1, Part 2. Thanks for listening. Have a good day.